All right. So we're going to zip through the first 29 slides that were parts 1, 2, and 2, and then we'll finish up the last slides for part 3. So this will be kind of a quick overview of what we covered. And we went into 3 different types of processes, and we can categorize nearly all processes into one of these 3 categories. And the most common type of process is self-regulating. And the flow loops are, of course, the most common type of loop, and they're self-regulating, but we tend to know how to deal with flow loops, and we have a good valve. So I tend to be more interested in the temperature, composition, pH control, and vessels and columns. And for these loops, the time constant to dead time ratio is greater than 4, and we want to classify that as near integrating, because in the response time with the PID sees, if the PID is tuned well and for minimum error, it tends to see what's going on in the 4 dead times and does its thing. So in the 4 dead times for this type of process, then it is still ramping. So it looks like an integrator, and we call it near integrating. So the more interesting loops, again, that I find that are self-regulating are actually near integrating, and these are typically for vessel and all types of vessels, whether they're crystallizers or reactors or evaporators or neutralizers, all types of vessels and all types of columns tend to have this near integrating response. And in the near integrating response, what the PID sees in its time frame, which is about 4 dead times, is a ramp. The equivalent open loop integrating process gain really helps us to go back and forth between, say, looking at an integrating process versus looking at a self-regulating process. And we can do this very easily by way of this simple relationship. And what I've recently found is that this relationship even works as a time constant is less than 4 times the dead time, and it's interesting enough, it even works if the time constant is less than the dead time, and it's becoming dead time dominant. That's kind of an interesting situation in terms of, and if you look at the ordinary differential equations, which you probably won't do, in any of my appendices, you can kind of understand for the generic form maybe what's happening at the very beginning. There's this ramp rate going on according to the time constant, or for a true integrator according to the integrating process gain, and you can convert back and forth using that very simple relationship here. Then we have a true integrating process, and of course the level being the classic, and where the difference between the flow that's going into and out of the level will cause the level to ramp. And here we see that with the controller manual is already ramping, and it's ramping in the opposite direction. So what we got to realize if a controller is in a manual, it's going to be ramping, and what we want to look at is the change in ramp rates as an indication of what the dead time is. So that's how we get that estimate of the dead time. It's kind of difficult unless you take into account what's happening here also with any resolution and noise band limits, but we can do it, and so we get an integrating process gain, that is the change in ramp rates here going on, and we do everything in percent because that's what the PID algorithm works in. And so if we divide the change in ramp rates in percent per second divided by the percent change in controller output that caused this change in ramp rates, then we get an open loop integrating process gain of percent per second per percent. And what we see in the literature is the fact that it's just, they can't spot the percent, it's just 1/2 that they give for the integrating process gain. But I think it's good to know where it really comes from and how do you end up with 1/2. Much less common is integrating than say integrating processes is the runaway process. But here we never want to see a runaway process that is accelerating within the 4 dead times. Well, if we have that, we have a very bad situation in poor design. So what happens is even for these runaway processes in the 4 dead times, it looks like a ramp rate. And we can use all the analysis and tuning tools that we have for integrating processes for runaway processes that would be actually accelerating. We can never run a test probably long enough to see that acceleration safely. Examples. Near integrating process, like I mentioned, if we have continuous columns and we're doing composition and temperature control, wherever it has composition, you can also add pH. Continuous vessels, composition and temperature control, crystallized vibrators, fermenters, neutralizers, reactors, a lot of different types of vessels. Now we have true integrating responses, and of course, level being a classic. And then for batch, we have composition, pressure, and temperature control as being true integrating processes. And if you look at it real closely in terms of the differential equations, they're maybe not quite true, but nobody's going to understand the slight distinction there. We think of them properly, I think, as integrating processes. Then we have runaway processes, and these are polymerization reactors, temperature control, highly exothermic, and you could take the position, well, this should never happen, it's poorly designed, but I've been in several polymer plants where it does happen. Polymer reactions just take off, and I've been in the control room where that happens, and what they do have is release systems, and if the reactor blows its contents over to the release system when things just take off and accelerate too much, and that has well, and it also has implications how we tune the controller. In those instances, we didn't use any interval action and used mostly a gain and derivative action to help prevent the runaway and getting into the acceleration. Biological reactor cell concentration control in the exponential growth rates technically could have a runaway response, some accelerations, but nobody's really doing that sort of concentration control that I know of, and the acceleration is so slow, hours to days, that it really isn't a concern. And then I personally have seen actually compressor speed control accelerate, and the only way we could stop it is within a tenth or 2/10 of a second, look at the rate of change of speed and take an action to shut down the compressor before it damaged the rotors. So we have that, and then so far as the PID controller sees, if you have a strong base, it doesn't really know beyond what's happening, and it sees an acceleration as you're approaching the neutral point. There's many loop objectives, and one of the things that's kind of interesting that I became very aware of is when hydrocarbon processing, someone maintained that the only, and this was the problem I had with the article, was that the only objective in tuning loops was to make sure you did not overshoot the final resting value of the PID output. Final resting value of the PID output is where it's going to end up to take care of the fact that there was a disturbance or you had to change the set point. And what he didn't realize is that the overshoot is necessary for set point load response for integrating the runaway processes. It's the only way you can achieve a new operating point or compensate for a disturbance to get it back to your current set point. And then we have a more detailed look at the loop objectives. We have the minimum peak error and the load response, and this has been more concern to me, even though I don't see it in the literature, in terms of preventing compressive surge, SI, safety instrumentated system, SIS activation, relief valves, rupture discs, relief valves themselves, undesirable reactions, and poor cell health. Most of what we see in the literature is on integrated error in terms of lower set point response, and you are minimizing the amount of lost product to enable closer operation from the set point. Then some people are very concerned about the overshoot of the set point, and here we would see that for compressive surge, or we're going to activate it SIS. But what I've seen particularly lately is poor cell health and how sensitive for the bioreactors that are on mammalian cell cultures, how sensitive they are to overshoot of the temperature set point, and to some degree also the pH set point. Extraordinary sensitivity, like a tenth of a degree overshoot, is a concern. Anyway, there's also that case in hydrocarbon processing, where you have overshoot of the FRV and the set point response, and these would be for truly self-regulating type loops, prevent interaction with heat integration, recycle loops, and typically see them in hydrocarbon processing. We want to minimize the time to reach set point if we want to minimize batch cycle time, startup time, transition time to new products and to new operating rates. We want to minimize split range processing. This is not well understood, but it's the point of greatest discontinuity, highest stiction in valves, and usually the highest nonlinearity in the valve gain. And so it causes poor control oscillations, and there's also wasted energy, reactants, reagents, and in the case of particularly mammalian cell cultures, poor cell health, due to salt buildup from sodium bicarbonate being added when it really isn't needed, and leads to high osmotic pressure where the cells actually burst. Then we have a really very important one. Some loops are oscillating just because of this. They don't know how to tune the level controller for particularly surge tanks just to keep the level within bounds, and not change the flow, manipulate flow so much, because that flow is a feed to downstream unit operations. And so it's upsetting them. So we want to maximize the absorption of variability in the level and minimize how much we move the valve that's being manipulated to control the level. And then to kind of generalize this, I look at this as like we're kind of optimizing the transfer of variability from control to manipulated variables. And controllers, we really don't make variability completely disappear. It's like we take it from an important variable and put it to a less important variable, and we have an optimum in terms of more general sense that we're trying to achieve. There are different worlds, hydrocarbon processing. I don't have that much experience in that, so it's kind of foreign to me. But for chemical batch and continuous processes where I spent most of my career, I tend to see this as having the near true integrating or runaway responses. And utility systems, of course, seen and worked with those because every process has some utility systems. And then I've worked on some polymer inline extrusion and sheet processes. I haven't really worked on pulp and paper or food. And I have worked on biological vessels, both fermenters and bioreactors. And these, as you read here, all have some rough distinctions. And Michelle mentioned that we really ought to have mineral processes here, which tend to be noisy, less well-defined, and difficult to categorize as a particular process, particularly if there's missing measurements, which may often be the case because of the difficulty making those measurements. Now, what we see in the literature is that often we just see a process time constant, process dead time, and a process gain. Well, really, there's all kinds of things in that loop contributing to it, and I like to see what those are. And so here I've broken it down, and this is even kind of a generalization. You could break it down in much finer detail in terms of where these dynamics come from in terms of the valve or variable speed drive, and then also the process, and the measurement and controller. And the good news is that by understanding this, we can maybe minimize the dead time, which is the source of most of our problems, And if most of the dead time is actually coming from the automation system, we, being responsible for it, have an opportunity to do something there. We would hope that the largest time constant, called T sub O, is hopefully the primary lag, the primary time constant, and so that's slowing down the effect of any disturbance here. Here we look at what is the reaction of the PID output to a set point change, and this is for a structure PID on error. And so we're going to see the effect of all the modes on the set point change, and we're not going to see the effect of feedback of the measurement because maybe a block file's closed, but we're just going to see what is the reaction here of the PID output in terms of the three modes to a set point change. And here we get a step in blue here from the proportional mode. We get kind of a kick. And since it's always filtered in industrial systems, what happens is it mitigates the size of the kick instead of being a big spike, and then it kind of decays out. So if we didn't have a filter, it would be a one-line spike here. Unfortunately, we do have a filter, and it's not such a big spike. It's a kick, and it decays out. Now we have the integrating action that's going on, and here after the seconds, that is the reset time, we have repeated the contribution from the proportional mode. So it's really seconds per repeat whenever they say seconds. It used to be like in some DCS systems or analog control systems, they would say repeats per second or repeats per minute. And then when they inverted it, they decided just to drop the word repeat. So today, in those systems where you have a reset time or an integral time, they don't say seconds for repeat. They just say seconds. But it's this action going on. Notice that it keeps driving and is never really satisfied. So why is the reset time set too small for near and true integrating runaway processes? And you can see in this example here, if the operator is looking at just digital values and he's seeing that the temperature is 48 degrees and the set point is 52 degrees, what he's going to think is, hey, the steam valve should be open. And really, if he had an understanding of the trajectory, then he would realize there is an overshoot going to happen, and really that the water valve needs to be open, which is what the PID controller, and most noticeably the proportional and derivative modes would do. The integral mode would be doing what he wants to do, which would be tend to drive the steam valve open because, hey, the temperature is below set point, and hey, I need more steam, and I'm not going to change that until after it's crossed set point. And then it's too late because then you have a dead time going on. So looking at digital values, humans think the steam valve should be open. What will happen if there is more, and that's what will happen if there's more reset than gain action. And so there's metrics for integrated and peak error, and here you can look at it geometrically. We won't get into the details, but basically the peak of this back-to-back right triangle is the peak error, the area is the integrated error for a given open loop disturbance, and it's kind of good to visualize this and then to realize what's happening if you aren't tuning it quite right. You're going to get a bigger peak error if the gain is smaller, and but you're going to get a slower return to set point if your reset time is larger than really it could be. Then we have the equation. Oops, yeah, well, let's look at set point response. And here we're looking at how long does it get to set point, and whether there's an overshoot here, and whether there is an undershoot, and these can be, let's say, different objectives or different types of processes. And the time to reach 63% of the set point change is the positive time constant, and that is a tuning parameter for Lambda tuning and also internal model control when we're using the self-regulating process tuning rules. This equation shows what you can do in terms of affecting that rise to set point, in terms of control of gain, feed forward, and how the integrating gain plays a role. And I can't get the set point faster than dead time, so we're going to add that all to what is the dead time. And also you're limited by how much of an output change can you make before you say you hit an output limit. If we look at the role of dead time and time constant, and we have integrating processes, we can kind of convert to equivalent time constant here to get to these equations. But anyway, we see what the ultimate limit is. We can't do better than this. We can't have a peak error that's smaller than this. We can't have an integrated error smaller than this. So we see peak errors are proportional to dead time, integrated errors proportional to the dead time squared. And unfortunately, that time constant, the largest in the loop, while ideally it's set by the process volume, it could be an electrode, a thermal wall lag, or a signal filter, giving you the false impression that you've done something good. What happens typically, though, is you'll tend to see very slow oscillations, and that's the clue you have a real problem. This equation can help you. If you have a large time constant in your automation system, and you wouldn't think of it being normally a problem, but hey, if you're talking about compressor pressure control or furnace pressure control, or if you have a foul pH electrode, or you have an improperly designed thermal well with an air gap, you're going to end up with a big filter. And you'd like to know what is the original amplitude, because you're seeing the filtered amplitude. You can use this simple equation, which is a Bode plot equation that becomes simpler because the time constant is considered to be greater than the oscillation period. And it's a way of understanding what the original amplitude is. It's also good for understanding the value of mixed volumes that are going to smooth out oscillations that are occurring here as the original amplitude. And this is quite a deal, at least in the type of processes that I get involved in the chemical industry, because there's these large mixed volumes, and then you may not be north reducing variability, because line of variability goes through the original volumes, and it's very much attenuated. Now, for pulp and paper and inline processes, and also in hydrocarbons, some of those processes, you don't have these volumes and until you get to the columns or the vessels. And so they are very concerned about oscillations and variability, because they never get really filtered. And so particularly with pulp and paper, those oscillations end up in the sheet. And so they have a whole different view of how important it is to reduce variability. Now, the ultimate limit is based on dynamics, but really what we're going to see is happening is based on how we tune the controller. In other words, if we foolishly tune the controller, it's as bad as if we have a lot of dead time. So here we're going to look at, well, what is the case in terms of peak error, and it shows how tuning the controller with its gain is going to help us. If we maximize the gain, we're going to reduce the peak error we see as a fraction of that open loop error. And then with the integrated error, it becomes a little bit more complicated. It's affected by both the reset time and the controller gain. But again, it shows the effect of those tuning settings, also the execution time of the PID and any filter you might have in the PID. When the filters haven't gotten too large, anyway. So these settings here show what the practical limit is, but remember they can't be better than what the ultimate limit is based on the dynamics. Dead time is the key. Without dead time, I would be out of a job. And it turns out we can look at it in terms of really how we want to set tuning settings. And that was one of the things not realized in lambda tuning by some people, was that really we want to focus on lambda, and it should be, if we're looking at internal model control, gamma, in terms of how big that is relative to a dead time, because that's the key. And the ultimate period is 2 to 4 times the dead time for self-regulating process, and for other processes, it can be a little different, but if we use a first order plus dead time approximation, it comes out to be about 4 times the dead time. Resonance can occur for oscillations between that 2 and 10 times the dead time, and scan PID execretion rate should not be 10. And oscillation periods greater than 10x the dead time are indicative of too low of a PID gain and some valve problems, which you can get from my article, white paper, Valve Response, Truth or Consequences, that is published just this year by Control Magazine. So we want to minimize dead time. These show the equations for doing that. So it's not so much you can accurately predict the dead time from these equations as it's telling you where the dead time is coming from, and therefore, and you get maybe an order of magnitude and what you might should be doing to minimize that. The toughest one, of course, to deal with is the sensor resolution or threshold sensitivity limit, because it depends upon the PV rate of change. How long does it take to get through that resolution or threshold sensitivity limit? Here, this shows that if we have an oscillation coming in as a disturbance, what's going to happen to it? Well, due to that filtering equation there, we see that actually if it's a fast oscillation, it gets attenuated, but there's nothing the PID loop can do. And the way to see what the PID loop is doing is compare the different color curves versus the brown, where the PID loop is a manual, and of course they're not doing anything. So it really can't do anything. Then we see here if the oscillations get close to the in period close to the ultimate period, then actually more control action causes amplification. And so if we're using what would be normally tuned as a good aggressive gain, we get quite a bit of amplification. And then we see what happens if the oscillations become a lot slower, and we find out, yes, we are getting a different story where now the amplitude is being somewhat reduced by that higher PID gain, and as we go on, we find for slower and slower oscillations, the high PID gain can essentially eliminate the effect of them. Now, the more common thing we think about, and this is what we're taught in control theory textbooks, is that, hey, if we have too much of a gain, we're going to end up with oscillations. And so here, yeah, we have oscillations that are relatively fast. The period is 30 seconds. The ultimate period is 42 seconds. And we see how just doubling the maximum PID gain causes really almost sustained oscillations here. And this is for near integrating processes. And it even gets worse for true integrating. And the oscillations don't die out at all for runaway processes. And it even becomes kind of distinctive in terms of the effect of PID gain in terms of halting and the approach back to set point there that is kind of a characteristic of too high of a PID gain. So you would think if a loop is oscillating, should we decrease the PID gain? Well, that's kind of what we're led to believe there. Well, here, look at a situation where now we have reduced the PID gain for that near integrated process. We have the same time scale, the same PV scale, and notice what's happening in terms of how the amplitude of the oscillations is much larger than we saw when we had the gain too high. Now, and if you're looking at, remember that equation for attenuation effect of volumes. If the oscillations are much faster, we get more of an attenuating effect from the mixed volume. Here, with these very slow oscillations, we get less attenuating effect, and the amplitude is larger. So we have more of a problem in terms of you seeing these oscillations downstream, and they can be so slow that they are just totally confusing in terms of really what's happening. And they get worse for true integrating and then for runaway processes. And we have a situation with backlash where decreasing the PID gain actually makes things worse. And so counterintuitive type situation. We have this window of allowable PID gains, and here let's look at the maximum gain. And for maximum gain, if we whatever tuning rule we use, it kind of reduces to this approximate relationship. For a smooth response, we want to keep the controller gain to be about 8/10 of the inverse of the product of the integrating process gain and the dead time. But if we just get a little bit more aggressive, we get into significant fast oscillations, and then if we get very aggressive, we get into severe fast oscillations. Now, what happens in terms of minimum gain? Well, here we have to include the reset time. And now if we look at this different expression here, we realize the controller gain has to be greater than 2 times the inverse of the product of the integrating process gain times the reset time. And what people tend to do is have too small of a reset time and not a large enough gain. So this is a very common situation that they get into. And if it becomes this situation here, violating this inequality, they become a very severe slope. So what's the solution? Here, part 3. So we're going to zip through part 3 very quickly. Lambda tuning rules, and the advantage here is we're going to intelligently set the reset time, and then we are going to set the controller gain. Now, the important thing is you got to do it in this order. If you decide, oh, I don't like that controller gain, and you change it, particularly if you make it smaller, you have messed up. If you want a smaller controller gain, you got to go back up here to the reset time and change it, and then go back to the controller gain. And this is how people get themselves into trouble. They may use these equations, and then they say, oh, I don't like that controller gain. It's too large, so they decrease it, and now they're in trouble, even though they've used these tuning rules. What I've done is modify the typical tuning rules that you get out this Lambda process that would set the rate time equal to the secondary time constant. Say, hey, if that's not identified, you don't have the software to do that, or it's small, we need to also have some rate time. And so I'm going to choose the maximum of either half the total dead time or the secondary time constant, whichever is larger. So setting the reset time first and then control gain for above tuning rules prevents violation of low gain limit. And if we can prevent the violation of high gain limit if the arrest time is greater than the maximum dead time. Now, I didn't talk too much about this arrest time, but it's different. When you move to integrating tuning rules, Lambda now is not a closed loop time constant, but it's an arrest time. And so instead of looking at the set point response, we're looking at the load rejection. And arrest time is, hey, we have a low disturbance, and it's diverting from us. And how long does it take to stop that excursion to the point where now it's going to say, hey, I'm going to start to return to set point, and that's the arrest time. So here we go with a new tuning objective that is now for near integrating, true integrating, runaway processes, is based on the ability to handle load disturbances. And whereas for self-regulating processes, the tuning objective, as we see later, will be for set point response. Now, tuning for level control, one of the things that's found useful is the full-scale resonance time. And you can approximate that as taking, like any resonance time, we think of in process design, is you take the total mass there and you divide it by the flow rate. So for this situation, we're going to take the maximum mass there, which will be based on the level, cross-sectional area, and density. And so we got this maximum mass, and we're going to divide it by the maximum flow rate, mass flow rate, and we're going to end up with a full-scale resonance time. And then we use that to determine what the arrest time should be, the lambda. And if if we were willing to, like, say we can take the full amount of that, what's available in that volume, basically Lambda would be that full-scale resonance time, but we can't generalize that. And so there's a maximum available level change, allowable level change between your operating point and, say, an alarm point. And then there's a maximum allowable PID output change from what you have now versus, say, an output limit. And so you plug those into the equation, and then it comes up with a more intelligent rest time. Now, if you have very tight level control, of course, the minimum, the maximum allowable level change would be a very small, and then you would end up with small lambda. But if you're talking about this case of surge tank level control, or wherever you want to maximize the absorption variability into the level measurement, and not be manipulating the downstream flow, then you end up with this multiplier here approaching 1, and you get a rest time that approaches the full-scale resonance time. Now you got to make sure when you're going for tight level control that lambda rest time should never be less than the dead time. Now we get into self-regulating processes, in pulp and paper and hydrocarbon processes and some polymer inline processes. These are important. And one thing I've done to modify them is that normally the reset time is equal to the time constant, but as you get into processes where the time constant is very small compared to the dead time dominant processes, you end up with a very small reset time. And when you plug that into the equation down here, this very small reset time ends up being a very small controller gain. You end up with kind of like interval-only control, and some people have complained about that. I don't have enough experience with dead time processes to say how big an issue it is, but to make it behave like we normally see for other tuning rules, we know that for if we want an appreciable gain, a proportional mode effect, that the integral time should not be less than about 40% of the dead time. So what I've done is modify the lambda tuning rules to say, hey, I'm going to take the maximum of that, so I'll never get into this interval-only type of control. And then if you plug this in, you end up with kind of the tuning you would get by other tuning rules, where it still maintains some proportional control. And note now that lambda is a closed time constant for a set point response. And for maximum unmeasured disturbance rejection, a lambda equal to dead time is used, yielding an equation seen in most other tuning methods. And actually, it's about half the Ziegler-Nichols reaction curve gain. So the tuning methods tend to converge and end up with a similar expression when we're looking for maximum disturbance rejection that's unmeasured, so we can't really use the feed forward. So if the primary time constant is greater than 1/2 the dead time, derivative action may be beneficial even here. So I've modified tuning rules to say, hey, I might want to use some derivative action. I'm not saying I'm going to use it, but if I am going to try it out, then I would set it equal to the same sort of relationship we've seen before from my modification of integrating process tuning rules, where we take into account which is larger, the secondary time constant, if we've identified it, or half of the dead time. So PID options. We have these type of options in many DCS systems today, and some TLC systems as well. We have integral deadband that stops integral action when it errors within the deadband. We have external reset feedback that prevents integral mode output from changing faster than response to the secondary PV or valve position. It's the key feature for suppressing oscillations from backlash, stiction, cascade rule violation, enabling move suppression, and enhanced PID. Basically, it says, hey, if whatever you manipulate is not changing, I'm not going to be using my integral action to keep driving it. So you have that, and then you have set point rate limits that help prevent behavior upsets to other loops by you moving your valves too fast. And so you can choose how gradual you want that to be, and then through external reset feedback, it recognizes that and does not try and do too much. And I can't emphasize how important this is. We're going to continue on here. The sectional reset feedback also enables the fact that we can have an enhanced PID that prevents the integral mode from changing the output if the PD is not updated, which can happen quite a bit with analyzers. PID structure enables users to specify what modes are active and whether they act only on changes in PV or also changes in set point. And then we got the reset windup limits. Actually, a lot of PIDs may not have this. That's kind of built into their output limit specification, but you can, in some of these PIDs, you can set those to be different than the output limits, and if you set them inside, they can provide faster recovery from heat transfer limits and get the valve open when there's solids buildup or high seal or seat friction. And then feed-forward control, we have flow and speed ratio control corrected by the PID. Advantages of PID proportional mode gain through PID options. The PID gain provides a more immediate response whose magnitude decreases as the PV approaches set point and stops changing if the process variable is settled. So it has that sort of intelligence of what's happening right now, whereas with the integral mode, it just keeps ramping in one direction or the other. Essential for minimizing peak error rise time, essential for missing self-regulation, and overdriving the output past the final resting value for integrating runaway processes. Essential in valve positioners to get immediate response. Reduces dead time oscillations and PID controllers from valve backlash and stiction and from measurement sensitivity and resolution. Judicious signal filter prevents valve movements from gain action on noise. PID output fluctuations are kept less than valve deadband resolution. Then we have external reset feedback that's turned on with back out. It's fast feedback of manipulated variable flow or valve position. And this enables us suppression of oscillations, violation of cascade rule, directional loop suppression, which has many opportunities here. I'm not going to get into. And, you don't want to violate the cascade rule, and you don't want to have overly aggressive tuning to be moving the output around too much. But given that this happens here, you can prevent yourself from getting into a lot of trouble just by turning this on and connecting up the back out. And you can even extend it to this case where if the PID gain can be as large as the inverse of the dead time down and open up self-regulating gain, which is incredible if you work through the tuning rules, if you use this external reset feedback. And it leads to this use of the enhanced PID when you have analyzers and you have a lot of dead time from them. So the procedure is determine loop objectives for the operators and process engineer, and the PID and manual track down, mitigate disturbances, and decide really what you should be doing with PID gain, whether it's increasing or decreasing it. For noise, use small PV filter, less than 2/10 of the dead time. Choose PID actions accordingly, and make sure you use the ISA standard form. Use signal characterization, DCF stealth linearized system, particularly for non-linear valve pH control. Identify the dynamics of different production rates, weather products, fouling, catalysts. That's going to change these values. Find the worst case. Determine if the process should be treated as an integrating or runaway. Tune for loop objectives. Using adaptive control is necessary to ensure the window of allowable gains is open enough for changes and unknowns. And I would go with what Shinsky said, which is first step the load response by momentarily putting the PID in manual, just for a second or two, making the output change, and finally, then after that, test the set point response as well. And you can use structure or a set point filter or set point relag to provide the speed of response to set point, but without much overshoot. For the PID structures, we got 8 of them. I really can't go into when you want to use each one of these, but they give you a lot of flexibility. The one here with the most flexibility is the last one, where you can set point weights, beta and gamma, and determine how much error affects the contribution of those proportional and rate modes. And if you don't want to see the effect of a kick on set point change from the derivative mode, then you would set gamma equal to 0. If you don't want the step from the proportional mode and step point change, you would set beta to 0. But you may want some, particularly with the proportional mode, you might want some movement just to help get you through the noise band or the stiction or the deadband from Backlash on a set point change. You want that initial immediate action, because we know from those equations for measurement dead time that as we make a more gradual change, we're going to see more dead time. Now, it's good to know that the beta and gamma factors, they're for the set point response. They do not affect the load response. Here it shows the effect of different betas on the set point response, and if you set beta equal to 1 here, you're going to have a lot of set point overshoot for tuning settings that were really designed for a load response and not a set point response. And you can see here, if we set beta equal to 0, we minimize that. Of course, you can tune this thing to be more friendly for a set point response, and you can also add in a set point filter to help with that as well. Here it shows the effect of those settings on the controller output, and you can see kind of a dramatic change as you change beta in terms of what the controller output's doing for those set point changes. Now we finish up with some really kind of intense stuff, because normally we don't see block diagrams for the time domain. What we see is a more concise, generic Laplace transform diagram. But, you know, when we program computers, and actually the way I like to think of things is get the equations for the time domain. And so what I did is made a representation of the different PID forms, and this series, also known as the real form, was what was in analog controllers and what was in the early DCSs, say, that came out in the early 80s. And I've added in the set point weights, beta and gamma, that show how they get into the algorithm and how you take that deltas and subtraction, you know, here going on between the set point and the PV to get an error, and how if beta is 0, you're not really considering the set point here, you're just considering the PV. But it gets a little complicated with the series form, because it's saying you're doing the derivative action first in series, and so it comes in here, and if this switches in the position where there is derivative action, it comes in here. It comes in here, affected by the gamma in terms of a set point weight for derivative action, and then it goes this route here. Note that the gain affects all the modes here, and it goes into the derivative calculation, and then comes here, and note it's summed here, and this is not something well understood, and people say, what, you know, but if you look at the time domain equations, you have to end up with the actual error here in the algorithm. So there is this other line coming in. But anyway, you go on from doing the calculation of the derivative mode, and you then do the calculations of the integral and proportional modes in parallel. Now, what we have also primarily in control literature and some PLCs, and some early DCSs may have given you this option, is what we call is an independent form. The last one, it turns out the settings, when you use derivatives, it would how much you set the derivative would affect the contribution from the proportional integral mode. You can't see that on the block diagram, by the way, to work out from the equations. And they're interacting in the time domain, but non-interacting in the frequency domain, as noted at the bottom of the slide. Now we move on to a parallel independence form. They say, well, we don't like that interaction. We just want one setting for the proportional mode, one setting for the integral mode, one setting derivative mode. So notice the gain setting doesn't affect the other two modes. This isn't used that much. What you have to realize if it is used, you need to be able to convert the settings and not get into trouble. So I don't advise using this, but if you have to use this, that's what you're stuck with. You got to realize the consequences. Now, the ISA standard form is what we think people should be using, and here it shows that the gain term does affect all of the modes, and everything is computed in parallel. There's a built-in derivative filter. Now, we'd like to look at using external reset feedback. And wow, this makes it complicated, and this is the only known time domain block diagram showing positive feedback implementation of integral mode with external reset feedback for the ISA standard form. Hector and I worked on this, and we had a lot of trouble. And in fact, what is published in my books isn't quite right. So here I'm going to, of course, do an errata to show this form, but this is what actually does work because I've tried this out and programmed it in the time domain. And it gets a little complicated, as you can imagine. The key thing is that the integral action is by means of positive feedback filter here, and the filter time is equal to reset time. And if we flip this switch, instead of it coming from the controller output, it comes from the external reset, say a secondary percent PV or a valve stroke. And it turns out then what we end up with here is not going to change if this is not changing. And it's hard to see how this all settles out. But for zero error, out one is zero, and the total contribution really has come for zero error, or approximately zero error, from here, the positive feedback implementation. So because we are adding this out to out one. So it's a real challenge, but I think the important message is that there are some controllers that have this positive feedback implementation. A curious aspect of this is that this was the only way you could do it in pneumatic controllers, because in pneumatic controllers we didn't have integrators. We had filters by means of restrictors and bellows. So we could implement a filter. So all pneumatic controllers had this. And then when we moved to electronic controllers, they said, oh, now we know we can make an integrator. And so they stopped doing this, not realizing all of the features that they lost. One manufacturer kept it all along. And then the DCS that I used, the first version didn't have it, but the second version realized the value of this and went to the positive feedback implementation of the integral mode. And that is the key to the proper operation of external reset feedback that is so important for so many different capabilities of the PID controller. So I realize this is all pretty intense, and if you don't understand this diagram, don't feel bad, because I don't think there's anybody else in the world that understands this diagram. So it takes time, but it is worth it if you can get into it. Okay, are there any questions? Oh, okay. All right. Okay. That has a choice of different tuning methods. Yeah. But, one of the things we learned is that we really want to set lambda in terms of a dead time, and it's not, I don't think it's the default that comes up. So you have to kind of go into the PID options and say, I want to set lambda, and I forgot exactly what the PID option is, but it's pretty obvious that, hey, lambda now is set in terms of dead time, or lambda can be set not as a factor. Maybe that was it. See, if you can just set lambda not as a factor of a time constant, or and for integrating processes, they try to make it as a factor of the integrating process gain. If you can set lambda not as a factor, but as an absolute value, then you can choose in your mind, hey, I want to set it, thinking of dead time. So if the dead time is 10 seconds, I would think, well, the fastest lambda I really ever want to consider is 10 seconds, but if I wanted to handle nonlinearities, I would go with maybe 20 or 30 seconds. If I go 2 to 3 dead times is providing more robustness and less oscillation. How about you, Matt Howard? Do you tend to use one tuning rule versus another? Yeah, you're right. I mean, I've worked on that, and we had to use a modification of the ultimate oscillation method. You never want to get true ultimate oscillations, but what we do is take the interval action essentially out of the picture by setting a very large interval time, seconds per repeat, or if it's repeats per second, a very small repeats per second, and increase the gain until we start to see a little oscillation, and then we say, oh, well, we know how high we can go in gain. We look at the oscillation period and we get a rough idea of what the interval time is. Yeah, we've done that. There's some, and that process can, and I've been in others that can ramp off scale in a second or two. You can't put it in manual. There's some thought that we could make a setpoint change and maybe figure it out from that, but what has worked is what I briefly described. How about you, Adrian? Have you, in your studies or any your applications? Yeah, and Shinsky, I'm actually a good friend of Shinsky. I've been to his home, and I have ultimate respect for him. And I tried to address his concerns, and one of his concerns was in terms of a near integrating, which I came up with that term. So that we could treat those processes as an integrating process tuning rules. And the other thing is, and rightly so, if you set lambda as a factor, say a time constant, you can get into a lot of trouble. And so my modifications to lambda tuning rules were largely in response to Shinsky. Now, then there's some things you can still do, and like I guess one of the modifications there prevents going to interval-only control. Interval-only control on a secondary loop is not the thing you want. You want a more immediate response from proportional action on a secondary loop. So that was one of the modifications I did, was prevent for those who go that way. And plus, I think you could use lambda tuning, but choose a lambda for the secondary loop that was 5 times faster, it's like 1/5 or smaller than the lambda for the primary loop, and you would then end up with a good tuning settings, particularly if you use the modifications that I sent or have shown here. The other thing is you could just tune that secondary loop, just to have a mostly proportional action and kind of do maybe this modified tuning method where, you take the reset out of the picture and then you increase the gain so you start to see an oscillation, and then you get that period that becomes your reset time, and then you back off a little bit maybe on the secondary PID gain. But what's interesting is, and it has been shown, that aggressive secondary loop, even to the point of oscillation, might be a good thing in terms of, particularly if there's a process time constant associated with the primary loop, that's going to attenuate those oscillations. If you really have a well-designed cascade loop, and there typically is this process time constant, and making the primary loop slower and attenuating oscillations. In that case, it's actually been shown you can have a secondary loop that's very aggressively tuned with a lot of gain action, and actually be kind of, could be oscillating if you were made a set point change to it, but the oscillations would have to be decaying, and it would actually help. Aggressive action would help the primary loop. So yeah, there is that concern out there still, and I guess I would say, yeah, be careful that if you use lambda tuning, first of all, use the modifications, and then make sure that secondary loop lambda is less than 1/5 the primary loop lambda, and maybe even go more towards, hey, let's try this check here of making sure we get aggressive control of the secondary loop with mostly proportional action. Yeah, good question. Yeah. Well, we would, when we did these tests, we would very closely monitor it, and I would increase the gain and make a little set point change to kind of get it moving. Yeah, get it moving. And then, because, otherwise you're waiting for something to happen, and you don't want to keep increasing the gain. So you make a very, you take the reset out of the picture, you make a very modest increase in gain, maybe 10%, 20%. Make a set point change, and look for, is there any oscillation? If there is an oscillation, and it's not decaying, you better decrease the gain right away. But if you, but saying that the oscillation is decaying, then you look at the period of that oscillation. Now, if it's very damped and it's like, oh, well, it's hardly an oscillation at all, you better make another change. So you get an oscillation that decays like every subsequent peak is 1/4 or maybe 1/10 or something, but something, there is a noticeable oscillation. And ideally they call quarter amplitude, where, it's like each successive peak is 1/4 of the last one. Then you get a period, and that period is going to be larger than the ultimate period. But all that does is give you a more conservative reset time, which I think is good. Yeah. So you're going to end up with a conservative reset time because that actual period you're measuring is much slower than the ultimate period. And so you put that in, and then you said, well, you know, did I like that slight little oscillation? If not, then you kind of back off and you know, and go with a little bit less gain. And then you test it again. Then you test it with the new gain, with the new reset setting, and just make sure that the oscillation is very little, and by making a little set point change. And, you know, you got to realize there's a compromise. When we go for minimum peak error, and what used to be, you know, they thought the best tuning settings was quarter amplitude decay. Now these days people say, oh, that's horrible. And what's interesting, like, you know, on the Automation Hall of Fame Awards, it has a quarter amplitude response on the trophy. And to show you how emotional an issue this is, people really got upset with that. And they say, you don't want that. Some processes don't want any oscillation. Which processes are those? It's, again, the ones where there's no attenuating liquid volume, well-mixed volumes downstream. So, you know, it could be hydrocarbon. It could be your situations where you don't get much attenuation, and it could be certainly pulp and paper, and they're very sensitive to any sort of oscillation, and that's when the Lambda tuning was originally developed. It was developed for pulp and paper, and they thought, oh, we don't want any oscillation at all, you know. And since then, they've kind of understood differently, but yeah. So, you know, a little bit of oscillations, as long as it doesn't get bigger for different operating conditions, and that's the concern, are you too close to the edge, but a little bit of oscillation is going to give you a smaller peak error for a disturbance. Yes, it is going to be an issue converting from a series form to a parallel ISA standard form if you have derivative action. If you don't have derivative action, it pretty much should be the same. In your version, though, with the older versions, you didn't have all the options of set point weight, gammas, and beta factors. So you really didn't have an opportunity of optimizing the set point response and, say, tuning it for a load response and then optimizing the set point response. You didn't have that option. So this opens up, you know, a possibility for you, the standard structure that often today is with the ISA standard form is proportional integral action on error, but derivative action on PV. So if there's a set point change, you are not going to get the kick from the derivative mode. So that's already kind of a default. In biological processes, they're so worried about overshoot, they will choose integral on error, proportional derivative on PV, so that there's no step, as well as no kick from a set point change. And they don't care how long it takes to get to set point, because maybe in the new biological processes, the batch takes 10 days, you know. So if it takes 15 minutes or 20 minutes more to get to temperature set point, who cares? And they're not going to change batch times anyway, no matter what. So, in terms of set point response. So, yeah, it's a situation where now you have a lot more options with the newer ones. But if the problem you get into is if you did use derivative action with a series controller, what happened is as you add more rate time, it counteracted the other modes, reduced the effect of the other modes, so you didn't get into trouble. So you can actually set a rate time setting as large or larger than the reset time in these older controllers. And remember, when I say reset, I'm saying seconds per repeat. So you got to think of what was the reset setting in terms of seconds per repeat. If the rate time is larger, even approaches the reset time in the ISA standard form, you're going to get into oscillations. Really severe oscillations, just due to the modes. There isn't this built-in interaction effect going on to help protect you against having too much of a rate setting. So a common problem is people, literally go from the series to the ISA standard form with too much rate action, and now they're oscillating really like crazy, very fast oscillations due to this rate action. And really, that's why in the modifications I say that the rate time should never be more than 1/4 the reset time. And I take that view because the rate time's kind of derivative's overrated, rate time's overrated. And I just want to be careful because I don't know what structure they're using. And even though I tell them, this is, you shouldn't do this, just to protect you in all cases, don't ever set the rate time more than 1/4 the reset time. Okay, guys, well, I'm going to check out the recording, and hopefully everything's okay. Thank you for participating. Thank you for the questions.